All right, so one last final quick video in this module, and it is about bond type and free rotation. So I'm going to start with the TLDR version, which is that single bonds allow for free rotation. So single bonds, this is good to remember this way, but it also helps because we're going to draw some orbital pictures in a second. We're talking about sigma bonds allow for free rotation. And double and triple bonds so specifically, right, what's different about double and triple bonds? It's when we have pi bonds, these restrict rotation. All right, so let's draw an orbital picture to see what this looks like. And so the orbital picture that we're going to look at is for this molecule. So it's going to be CH2Cl, CH2Cl, if we had kind of a condensed formula picture. So two carbons connected, and each carbon has two hydrogens and two chlorines. And well, let's go ahead and put in my lone pairs on chlorine so we're complete. And I'm going to draw a picture that shows you why it doesn't matter that I've drawn those two chlorines both on the bottom of my picture. I could have drawn one chlorine on the top and one on the bottom, or two on the top, and you would have the exact same molecule. So the reason for this is if we really quickly think through what my hybridization would look like, each carbon is sp3 hybridized, and that carbon-carbon single bond is going to be a carbon sp3, carbon sp3 single bond. So what that looks like, got a carbon sp3, carbon sp3 single bond. And if this perspective-wise is here, then what the rest of my picture looks like is that I've got, let's see how I want to do this, a bond going back, a bond in the plane of the paper, and a bond coming out, right, for everything to be 109.5 degrees away from each other. So going back in the paper and coming out. And connected to that, I have two hydrogens and a chlorine, and two hydrogens and a chlorine. So what the free rotation is saying is that this carbon-carbon bond can rotate, which means that these three things, let's hold this one on the left stationary. If you rotate this carbon on the right, these three positions can exchange with each other, but it doesn't make any change to the molecule because the overlap is not affected by rotation. All right. Let's look at the version of this molecule with a double bond. Now, this will also happen with triple bonds, but it will be for the exact same reasons. So if we do CHCl, I'm going to put my two hydrogens up top, and this time put my chlorines on the bottom. And this is different than if one of my chlorines was on the top and one was on the bottom. Now, if they were both on the top, I could just flip my whole molecule over and it would be the same one that I have right here. So if I take this picture, now my single bond is still going to be that pointed overlap, except now when I have steric number of 3 So I have sp2s pointed at each other to make that single bond. My double bond is the one that is really important here. So it's the pi component of that double bond. So I'm going to draw my molecule picture rotated. All right, carbon, carbon. I'm going to rotate it this way. So hydrogen going back, Cl coming out. Hydrogen going back, Cl coming out. And this pi bond is a p orbital here and a p orbital here. All right, I'm going to draw the lines because I didn't draw my atoms close enough together to show them attached. If now I start to do this rotation, the result is, all right, if I'm holding the one on the left stationary, still carbon with hydrogen going back and a Cl coming out, connected to this carbon. And if I'm rotating it, right, tipping everything forward, I've taken that hydrogen in the back and brought it up into the plane of the paper. And then my chlorine has gone from coming out, and now it is pushed into the plane of the paper, which the way that leaves my orbitals, this p orbital on the left carbon hasn't moved because that atom hasn't moved, but my p orbital that was in the plane of the paper, if I rotate this carbon, it's now coming out and going back. So there's no overlap here. So there's no pi bond. So you can't rotate in a pi bond without breaking the pi bond. So no overlap equals no bond. I'm not going to say there's absolutely zero rotation, because if you put enough energy into it, you could get it to go. But what we call this is restricted rotation. So you will, for the most part, not see it at all because it would result in breaking the bond. And so what that means is that in our case that had the single bond, you could draw that picture any way you wanted. For our case here that has the double bond, if we draw the version that we did, right, with both of the hydrogens on the same side of the double bond, my chlorine's down, it is different from if we were to draw this molecule with hydrogen and hydrogen on opposite sides and the chlorines on opposite sides. And this is different enough that we have different ways of naming it. So the one on the left is cis, and then you don't need to know how to name this, but I'll give it to you so that you have it. It is 1,2-dichloroethene. But this is the important part here, right? They're on the same side, so they are cis. And then this is trans, 1,2-dichloroethene.